Let us discuss more details about Gaussian naive Bayes by using an example. Let us consider this data. We have 6 persons with their height, and we are classifying into 2 classes, fit or unfit, based on their height. So here the height is continuous, which means that it can take any value, any real value. So we would like to classify for any new unseen data into one of these categories based on this information. Let us consider a new height which is 178 centimeter, which we would like to classify into one of these classes as fit or unfit. So first we compute these two probabilities, probability of fit given height as 178 and also probability of unfit given height as 178. So whichever probability is more, we kind of classify this height data point to that particular class. So in order to find these probabilities, which are actually the posterior probabilities as per these naive Bayes. So in order to do that, we need to first get the priors, evidence, likelihood function, all those things. So first let's compute the priors for this. So as you can see here, we have in total 6 points. Out of that, there are 3 points belonging to fit, 4 and 3 points belonging to unfit. So the probabilities would be 3 by 6 and 3 by 6. So once we have found the prior probabilities, let's compute now the likelihood function and likelihood probabilities and also the evidence probabilities. So likelihood probabilities we can know only when we know the Gaussian distribution. So we don't have any details regarding distribution except that we have these few samples. So there are two classes. One is fit class and unfit class. Both we in Gaussian naive Bayes, we assume that both of them come from a Gaussian distribution. So in order to find out the parameters of the Gaussian distribution, we utilize the maximum likelihood estimates of those distribution. So we use the samples to compute the MLE estimates of mean and MLE estimate of variance, and thereby later we compute the likelihood probabilities. So in order to do that, so these are the 3 samples we have for the fit class and 3 samples for unfit class. So sample mean for this is given as follows. Which is taking out the average and dividing by n. So this is the maximum likelihood estimate of the mean for the Gaussian distribution, and this is the maximum likelihood estimate for the variance for the Gaussian distribution. But you have to note that this is a biased estimate. We also have one more thing, which is an unbiased estimate, where we divide by 1 by n minus 1. But when n is large, they become more or less same. In the main famous packages, Python packages like sklearn, they use 1 by n, but for large values of n, it does not matter. So but basically we have these two estimates, and we are going to use this mean estimate and also the variance estimate to find out the Gaussian distribution and thereby compute the likelihood values. Let us compute the sample mean and sample variance for each class. So we have 3 points. So if you take the average of those 3 points, we get the sample mean, and if you take the variance, compute the variance of those 3 points with respect to the sample mean, we get the variance value. So we can do the same thing for unfit class. So once we know both these parameters, we almost know the distributions completely. So Gaussian distributions can be characterized by these two parameters. So once we know this, our goal is to find out for some unknown value, something like 178 centimeter, whether it belongs to class fit or class unfit. So let us see how we can find it. So let's compute the value of the probability for the data point height as 178. So when you compute this likelihood, so for fit class, x would be 178, and we have the parameters mu and sigma square. So the probability of 178 given fit, which is this is a Gaussian distribution. So this likelihood probability is actually a Gaussian distribution, and we using the Gaussian tables, we can compute the value of these. So that would be 0.074. So in the same way, when we compute for the unfit class, with a mean of 155 and variance as 16.67. So we get very low probability. So by this itself we could say actually that this has more probability, but we know how to classify. So we compute the product of these priors and the likelihood function. So posterior probability we get it, we posterior probabilities we compute based upon the priors, likelihood probabilities and the evidence, but we know that denominator is not needed, so we are just using the prior probabilities and the likelihood function. So when you multiply this, we get this is a probability 0.037, and when you multiply this we get a very low value. So by just comparing this, although these two values are not actually the posterior probabilities because there is a evidence term which should be in the denominator, but since it is common for both these terms, for comparison it is enough for us to find out just the numerator and find out which class it belongs to. So since this value is more, we say that 178 belongs to class fit. So by graph also we can see here it is lying here. So there is a certain non-zero probability for 178 for even the unfit class, but it is very low. It's just that the probability that 178 belonging to fit class is more as compared to unfit class. So this is how we try to compute the posterior scores and thereby determine which class it belongs to. So this is how Gaussian naive Bayes works, and so this is what we have done. And so let us now see the overall summary. If it is 178, it is falling somewhere here. What if the value is 165, which is exactly in between? So when it is exactly in between, or when the probabilities are same, we cannot conclude anything whether it belongs to unfit or fit class. So based upon at which point it falls under, we can determine which class the new data point belongs to. So this is how Gaussian naive Bayes, which is a supervised machine learning algorithm, utilizes the labels and the data points to compute the priors, likelihood function, and its estimates like sample mean and sample variance. And later during the classification or during the testing stage, we use the same probabilities to compute the posterior probability and determine which class it belongs to. So this is how Gaussian naive Bayes works. Here, instead of raw data, we have already computed priors and also the statistics. So there are three classes: apple, orange and banana, and we are supposed to find the new fruit to which class it belongs to depending upon its parameters, weight and diameter. So our goal is to find out the which fruit it belongs to. Given the data what we have is the weight is 140 grams and diameter is 6 centimeter. So we know we need to find out the likelihood probabilities, and we also know that likelihood probabilities are Gaussian distributed with its appropriate mean and variance parameters. So we have been given each of the mean and variance parameters for each of this class. Now we need to find out to which class this is most probable. So in order to do that, so first we will be computing for each class the posterior probabilities, which is the multiplication of the prior probabilities and the likelihood probabilities. We know that features are independent, so they have been written as product here. And so if you compute the score for apple, we will be having prior probability of apple into probability of 140 weight given apple and probability of 6 diameter given apple. So when you compute these values, we get as follows: 0.00176, and these values we get it using the Gaussian tables. So we know that this is Gaussian distribution and its parameters, mean and variance, also we know it. So therefore using the tables we compute these values. In the same way for orange we compute it, and also for banana we compute it. So out of these three, we can clearly see that apple is having the highest posterior score, and therefore we classify the new fruit belongs to the apple. So this is what the predicted class is apple. important thing to note is we never computed the denominator, which is the evidence, because it is common across all the classes. So we are only finding the numerator. That's why we are calling it as posterior scores instead of posterior probabilities.